All right, good morning, and thank you for joining us for this webinar of the US MAP Consortium. We're going to get started with all the good technical details here in just a second, but I've got a few quick housekeeping items to run through before we can kick things off. To answer our most asked question, yes, a copy of this presentation will be available on the US MAP site in a week or two. We just have to process the recording and get it put up there. So if you see anything interesting today, you'll be able to go back and check it out again once we post it there. If any of you are having audio issues or other weird issues, the most common fix for those kind of issues that we see is switching from computer audio to phone audio. If problems persist, you can either first type your question to the chat there on the GoToWebinar control panel on the right side of your screen. I'll do my best to help you answer it. And if I can't, you can always contact GoToWebinar technical support at the number shown there. We are going to be taking questions for a presenter at the end of the presentation. So if you have a question at any point during the presentation, just type it into that questions panel. We'll keep an eye on those as they come in, and we will do our best to answer as many as possible at the end of the webinar. Finally, I just want to note, because sometimes we get some confusion over this, if you have a colleague or a friend who might also want to see this webinar and they haven't registered yet, don't worry, it's not too late. If you just share that GoToWebinar registration link with them, they can join and come into the webinar at any point during the presentation. So with that, I'm going to hand it over to Joe Barry, who's going to introduce our speaker while we get our speaker's slides queued up. Thanks for joining us.
Well, welcome everybody to this second US MAP presentation and webinar. It's a great privilege today to introduce Dr. Michael Irwin of Hunt Perovskite Technologies, who will be our presenter today. I got to know Michael from his work as a graduate student when I was a young staff member, because he was actually working on some competing activities at another institution with some of our contact layer work. And then I had the privilege of meeting him it's almost a full decade ago now at an ICMR workshop on thin film solar cell materials that was held at Santa Barbara. And we had kept in contact off and on since then. And when he moved to Hunt to begin looking at solar cell applications for them, we started a partnership on a number of different technical activities. So it's been a lot of fun working with him, and he's going to talk today about de-risking metal halide perovskite semiconductors for PV applications. So it's with that, I'll turn it over to Michael and take it away.
Thanks, Joe, for the introduction. Really appreciate it. So thanks everyone for joining today. Hunt Perovskite Technologies has been around for about 7 years or so, and our core focus since the beginning is on the most important question I feel in perovskite technology, metal halide perovskite technology, and it is the material itself. Is the perovskite semiconductor viable in these applications, in particular solar PV? Is it a viable semiconductor? We know we can build these different stacks, right? We have these different devices, thin film devices that have been constructed, and you can buy them today in cadmium telluride. CAD panels are available, been researched for a long time. So we know how to build a thin film device, but can perovskite actually function in that role of cadmium telluride? But something that has a lot of benefits, cost and otherwise they'll get into. And so that's the approach we've taken. So from the early days, it was clear that the perovskite semiconductor made an excellent PV cell in terms of efficiency. The efficiencies rose very, very quickly. The record cell, 25.4% out of Korea, exceeds both of more now legacy thin film and cadmium telluride and SIGs. So we know there's lots of value, but everyone knows that the system is not durable. So since the beginning, we've always focused on the durability of the perovskite, but from a fundamental standpoint, in order to build a strong foundation for a solar technology. So that's what we're going to focus on a little bit more today than some of my earlier presentations on the material itself and some of the approaches. So real quick, who is Hunt? It's in our name. Hunt Perovskite Technologies. Hunt's been around since 1934. It's an oil and gas company, originally based out of East Texas, my neck of the woods. But now it's currently headquartered in downtown Dallas. It's got a quite diverse portfolio, even though it's originally an oil and gas company. We are also involved in power operations, real estate, other investments, ranching, and so on. But it's a great company, been around for a very long time, family owned, still owned by the Hunt family. Something that's not very common, right? To be family owned and be able to persist such a long time really shows the strength of the company as a whole and the leadership that drives it. So, overview of the company. I mentioned some of this, but what are some of our kind of claims to fame? Well, you know, we've been in stealth mode the entire time, right? So there hasn't really been an opportunity to share with others what we were doing. So some of the things that we've been able to accomplish is one, first we know of, isolate the pure alpha phase form of modinium lead iodide. Back in 2015, we were an early adopter of the PI in architecture, something that a lot of folks switched to a few years ago, but it took quite some time. We have one of the largest patent portfolios in the space. We've been an avid filer, but we've also been avid inventors to be able to do so. All of our processes, even though this is more of a lab scale at the current time, are all commercially scalable methods. We have scuttled other things that are not feasible for commercialization. Further, we focus on high throughput durability testing. We'll get into some of that in a moment. And then at the core, you know, like I said in the beginning, I value a strong foundation. That is how great organizations are built, and it's built on the shoulders of really wonderful individuals who comprise the Hunt Perovskite team. A couple of facility, our lab is actually in downtown Dallas. This is an empty space. We've built bespoke for this application. So it's got optimized egress and space for things like slot die coaters, vacuum laminators, like you can see in the lower left-hand corner. So the matter at hand, metal halide perovskites. So I like to present this part in terms of the HPT perovskite, not just perovskite in general. For those on the line, you know that perovskite is actually a crystal structure. It's not a material. And so to avoid the misnomer, I like to talk about what is the Hunt perovskite? What is its value proposition? And asked this question many times. The best answer I have for us, what I feel is the most compelling for what we do, is we have developed a revolutionary new class of ink-based, printable, yet high-performance semiconductors. We know those two things are individually possible. You can print a semiconductor like a organic photovoltaic. This is what I got my PhD on. You can make a high-performance semiconductor in gallium arsenide. This has both been done, but can you do them both together at the same time? And in my opinion, no. You have never been able to do this until Hunt perovskites, until the metal halide perovskites came into being. So our particular value proposition, people do. There are other people working on this, other startups, large corporations working on perovskites. They have different approaches. Our approach is we're trying to utilize additive manufacturing techniques to leverage Industry 4.0, automation, printing in an additive way. So you print the material just where it needs to be, not where you don't, right? So that it makes cleaning easier, patterning is easier, and it's more conservative, the material you have to extrude in the process, so it keeps costs down. That leads into a very low OPEX, but more importantly here, a low CAPEX of less than 8 cents per watt, so that's less than $80 million per gigawatt, and a panel cost of less than 9 cents per watt based on current materials and without leveraging additional economies of scale that would come to be once the printed technology, printed semiconductors becomes more mainstream. Also a small footprint of the factory. That again is in part due to the printers, the slot die printers that you would use, high throughput manufacturing and inexpensive materials. And also I think from a social standpoint, you have to be aware of what it takes to make your materials. And so even in the case of a battery, we've talked a lot about cobalt and how the cobalt can come from places that have significant political and labor issues. Also lithium, right? Lithium has to be mined and still has to be mined. Elon Musk is talking about mining basically the entirety of Nevada to produce enough lithium to drive his gigafactory. And that's great because we all need electric cars, I think, but at what cost, right? So everything that's in the perovskite solar cell is not only readily available, but also cheap, right? So the lead, we would never need to mine for lead. You only need a very small fraction of lead currently in the recycling stream from lead acid batteries to produce terawatts of power. But again, with all these virtues, there's always a catch, right? There's no free lunch. And here the cost of lunch is durability. So we got to focus in on how to make this material durable, how to make the cell durable, and how to make the module durable, most importantly in that order. And so our two primary approaches to date have been on materials level durability and then device level durability. We're focusing on module level durability, but we didn't feel that was important until we had a durable material, that strong foundation that I say is so important, that I believe is so important, and then the device level. The perovskite is a unique material compared to other semiconductors, and so it has unique considerations for its stack. Now, nothing particularly, I would say, special, just unique. So all solvable problems. And so in the durability side of materials, we have composition of matter. So the cubic FAPBI3, ink chemistry, because this is printed, and so you have to have an ink, right? So the precursors are dissolved in a solvent, and they have some additives all mixed in. This is printed and then annealed in some form or fashion to make the semiconductor in situ on the substrate surface, similar to what you can see in the lower right-hand corner, cross-sectional scanning electron microscope image of one of our perovskite materials to highlight processing. You know, if you process well, you can make the perovskite very flat, and then also the architecture. And we have patent protection in all 4 of these core pillar areas. So today, like I said, I want to talk more about the perovskite material itself. You know, there's a certain sex appeal with efficiency. I think that people love to focus on efficiency, but to be efficient and to be durable all at the same time, that takes something special, right? You can be efficient and not durable, and durable but not efficient. Those are not all that hard. People can make high efficiency cells, but can you put them on a roof or in a field and have them last 30 years? I don't believe that is the case. And so you have to get both into the same bucket. That's really important. So I will admit chemistry is used on this slide 3 times. I am a chemist. I love chemistry. Chemistry is really fun. When I get to do chemistry in my job, it's the best part of my day, in addition to electrical engineering, mechanical engineering, and so forth. But we're going to look at bulk chemistry, defect chemistry, and then the surface and grain boundary chemistry. Now, obviously, this is not a 10-hour talk. This is not a lecture series. It's just one talk. So we'll only touch on these 3 different areas, but these are the approaches we've taken to be able to establish this robust perovskite material. So starting off with bulk chemistry, that's the one I think that most people focus on currently. And in our case here, we're utilizing formamidinium lead iodide. I'll make no secret of that. What's actually in it is where the IP lies. So in this case here, you can see it starts at the top as a pure FAPBI3 material that is loaded into a damp heat oven. It's sitting at 85 degrees Celsius, 55% relative humidity at 85 C. So this is a very nasty environment. And so we took our pure material, put it into this environment unprotected. There's no coatings, no encapsulation, no nothing. It's just the bare naked material in this oven. And you can see actually it stays quite robust for up to almost 300 or so hours. It persists, but not this 1,000-hour magical marker number we like to rely on. And so there's a particular additive, no, I won't tell you what it is, that we put in an increasing concentration going down the slide. And you can see when we got to the final concentration X, the material persists for over 1,000 hours. You can see some color change there. That's mostly from mass translation. That's not actually from degradation. The material by spectroscopy is all still there. Further, we have a nice little Anton parse setup that I'll talk about in a minute for our XRD, our thin film XRD, and it allows us to load materials in control the atmosphere and the temperature of the stage. And you can see in this case here, that same material without the additive, we put it into the Anton par, we can get up to about 135 Celsius, and it starts to decompose a little bit. You start to get a little lead iodide peak. But then, which is denoted there about 13 degrees to theta and the diffraction pattern. And then we put this into the original ink, allowing it to incorporate into the solid, and we can heat it all the way to 195 and the material remains stable. There is a little wiggle of lead iodide there, but nothing as prominent as we see here with no additive. Again, all the peaks are highlighted and labeled there across the top of the diffraction pattern, lead iodide pointed out. Big improvement, right? 195 Celsius is not a problem for this material that had previously 135 started an issue. This was something that was really common in the literature back in the early days. You would, I think Joe actually showed me this data first before, or these data first before they were published, that, you know, in the annealing process, you actually had an intersection between annealing and degradation where the material would actually start to degrade before it fully annealed. And that's, you know, certainly an issue, right? If you can't fully anneal it, form the perovskite in situ by which the process progresses, then you'll never make as good a perovskite as you can. So you got to be able to isolate these two things. So having this high threshold of 195 C allows a large window of processing temperatures. Next, also with XRD, we had noted in the past, also in the literature, but in our own samples, particularly in the early days, you'd actually see lead metal, crystalline metal in the SCC structure grow in to the thin film diffraction pattern. You're like, well, how in the heck are we making lead metal? And so this, to me, seemed like a great opportunity to dig into the durability in a unique way. So we took this Anton par attachment, it's there in the right-hand side. It's right here. And you can see the stage there kind of nested inside this temperature controlled stage. And what we did is we loaded the sample in. We have 4 different incidences here, and we exposed it to different atmospheres. And I believe this is 75 Celsius persistent. And under oxygen, you can see in the upper right-hand corner here that the despacing of the perovskite unit cell decreases significantly over time. Now, that is also supported here. You can see that actually over the course of about 50 hours, the perovskite actually decomposes. In this case here, this is open atmosphere, the one I just drew the arrow on, versus a pure oxygen atmosphere in the upper left-hand corner. And you can see that all the perovskite peaks, this is the intensities, the summation of the signal intensities, or just the 001 peak, which is the preferred orientation of the material. See, they decrease with time to about 50 hours while the signal for lead iodide increases. But then the signal for lead iodide also decreases. So where in the heck is the lead iodide going, right? That's a big question. But certainly under this elevated temperature, under the bombardment of X-rays in an oxygen atmosphere, we have an issue, right? So we tried it again here in vacuum, right? So we did an inert atmosphere, so just no atmosphere, right? So it's just under a vacuum, so no minimum number of gaseous moieties floating in the air. And you can see there is no change in the despacing over the course of this 50-hour period from left to right. In fact, there's actually a volume increase. We think that's important. I won't get into those details today, but we think that's actually important and relates to the defect structure. Now, what happens if you take the sample and heat it in vacuum, under vacuum conditions, and then expose it to oxygen? Is there something we're doing to achieve a unit cell volume increase that's irreversible? Are we changing the material in a fundamental way? And you can see now we expose the system to oxygen right after being under vacuum, and you get the same change in the unit cell volume as you do if you just do oxygen by itself. So it's not solvent degassing or any of that kind of stuff, things that would be irreversible. there's something different going on under vacuum. The material is changing in a different but yet positive way under vacuum versus the negative way it changes under oxygen. Same thing under nitrogen. We also have this reduction in the despacing over time with exposure, but not as intense as with oxygen. So what do we think is happening? So starting here, reaction 4 and 5, this is kind of the supposition that the H nu here being X-ray photons are creating some sort of a plasma. Create free electrons near the surface that can react. Nil is the initial perovskite, unaffected perovskite. This electron can react with the surface in some way to create iodide and Fa vacancies, reform the helium, making a catalytic reaction, but this results in the loss of FAI. So the vacancies represent the new material, the new perovskite material that now contains these vacancies, and the FAI is a species that has left the system. So again, we have this kind of cyclic system here that is resulting in vacancies, and these vacancies at some point will decompose the material. And so you can see here to the left of that 3 other reactions where you have kind of standard decomposition in reaction 1, so FAPBI3 decomposing into lead, iodide, and FAI. This is the opposite of how it's formed. But if you form Schottky defects in some way, i.e. what's to the right here, this is a different way for it to decompose. And then you have more pure FAPBI3 without vacancies react with this material with the vacancies. So the vacancies cause an overall decomposition to lead iodide. And that's another way for us to get to that final decomposed product. So loss of FAI and the creation of lead iodide. So I did mention the creation of lead 0 also. I'll come back to that with a different data set. So defect chemistry. Our defect chemistry approaches, there are several. Today, I will only focus in on density functional theory. And so we have some atomistic representations here of perovskite. The those along the top are monomorphic, meaning that you add a defect and you maintain the cubic structure. So everything's at 90 degrees. A is equal to B is equal to C. And then we have polymorphic. So you add the defect going from D to E to F. And then we allow the structure to relax or undergo polymorphism. And this is really important. And so the energetics of a monomorphic defect versus the energetics of a polymorphic defect will be highlighted in the slides to follow. So one of the ways is that when we've kind of covered here with XRD, the XRD approach is vacancy-mediated degradation. So again, nil, that's the initial perovskite, that's the cube here, or the supercell we're using for our DFT calculation. And we show what happens if we form these same Schottky defects. We remove an FA and an I separately. We represent them as one here combined, but we have now in this structure an FA and an I vacancy. So if the monomorphic degradation, you actually have a exothermic reaction, very small, but there's a little bit of energy release there, negative 60 MeV for the delta H. But if it's polymorphic, it's actually quite positive, 810 millieV. I had shown previously that you can actually assist this process, since it's now endothermic, by the addition of water. It'll actually lower the energetics required to lose the FAI, but we're not going to show that today. Now, but if you can form those vacancies, if you are able to have the extra energy to allow them to form, then this decomposition from FAI or FAPBI3 to lead iodide becomes highly exothermic, negative 800 MeV. So in the polymorphic state. So once you have the vacancies present, these now mediate and guide the reaction forward in degradation from FAPBI3 to lead iodide. So this may be obvious for those who make devices, but now we know exactly, or we have a very good idea of one source. So if we can control the defects, it's not just about efficiency, right? It's not just about mid-gap states, defects that form that interject states into the conduction band, these low energy states, mid gap states, whatever. It's also about durability. So the defects here play a much larger role in the ability for this material to make it to market than initially thought. Initially, so Xerxes Stir published a paper, and others have, that show that these defects that form, the iodide vacancies in particular, result in these shallow traps at the conduction band, if I'm not mistaken. So if it's a shallow trap, it falls in there with the conduction band, it probably won't cause a problem, right? You don't have mid-gap states that will act as charge traps. So yeah, so who cares, right? Who cares if there's defects, because this material now is defect tolerant? Sure, energetically, but not structurally. Structurally, this is bad news. So it has to be addressed to make the material durable. Further, there's another issue that's near and dear to my heart. I firmly believe there's an amorphous material that comprises the perovskite thin film. We know there's a crystalline material, there are crystallites, there are grains. That is the perovskite itself. But there's a second fraction to the thin film that exists that I believe is actually important. I refer to it internally, colloquially, as the glue. It kind of holds it all together. But there is something that I believe is super stoichiometric FAPBI3 that exists outside of the crystallites. If you don't have this material, you don't have a good functioning material. Now the problem is that you have an exchange, right? So you have this super stoichiometric material that lies on the surface or in the grain boundaries, and it can go from there into the crystallite, and the crystallite can move mass, translate mass from inside itself into the grain boundary. So you have this exchange. And so we've been doing some calculations, DFT calculations, to represent this, but this is more a transition to the next stage here, where we want to focus in on those components, the surface and grain boundary chemistry. So we've been able to link perovskite stoichiometry to durability. Now, this may sound like a bulk attribute, but in reality, I think this is a surface attribute, because even when you modify the perovskite's stoichiometry, quote unquote, it still functions as a solar cell. So the bulk, the internal, like the Tootsie Pop, the caramel center is still caramel, right? We're not really affecting it. It's the crunchy outside candy that we're affecting. And so when we say we're losing FAI, where are we losing it from? Not from the middle, we're losing it from the outside. So again, this is why I think perovskite stoichiometry is more of a surface property, grain boundary property, than that of a bulk within our context here. So there's two things we've been able to come to understand. So first is that if you have a super stoichiometric film, as represented here as a swing to the left, we actually get a relatively high low frequency capacitance here, say close to 200 nanofarads per centimeter squared by admittance spectroscopy, whereas a good functioning cell in our case is closer, what we believe is stoichiometric material is closer to 100 down here. So we believe this is related to this, and this is related to this, or probably maybe somewhere in the middle. Can't go too crazy. So if you have too much AX of the ABX3 structure, you get this high low frequency capacitance. If it's stoichiometric, you get a lower one. Further, if you swing to the other side, we have the opposite issue. Now we have excess BX2, in this case lead iodide. Lead iodide is also a semiconductor. It's a wide bandgap semiconductor, around what, 2 eV-ish, something like that. See here in our spectral response to the right, that is the red edge, or the low energy edge of the spectral response of the lead iodide, producing what we call internally the lead iodide shadow. So if you have too much lead iodide in your system, you actually see a reduction in the spectral response at less than 500 nanometers. So we have two really great kind of key indicators from our other battery of tests that give us a strong indication of what the stoichiometry of the surface of our material is. So how does this reflect on durability, right? That's the big question. There's been papers published that show that maybe a little bit of extra lead iodide, right? You kind of overbake your film, you form this lead iodide shell, and it improves your durability. This is an older thought. I don't know if this really persists as much in academic circles, but it's clear here on the right, if you do have too much lead iodide, that if you take our cells, and we're stressing these under light plus heat, so this is one sun light intensity at 75 degrees Celsius, persistent and concurrent. You can see these cells quickly decompose in around 25 hours. They just die right away. And we can see why here. So the spectral response of those same cells show a very strong lead iodide shadow. Counter to that, we have the same but opposite effect. We have a high capacitance there at the low frequency response in the admittance spectroscopy. And these cells also decompose very quickly, about the same kind of time frame. But we also have two cells on the same substrate that have a proper stoichiometric low frequency capacitance, and those persist. So even on the same substrate, we're able to, by doing certain things in the process, we can control stoichiometry across the substrate to make it super stoichiometric in one location and stoichiometric in another location, make devices out of that, and see the response. And that's one of the things that we did here, though I will admit this was not on purpose. This was found in the aftermath, but we can do it on purpose now, but in this case it wasn't. But it's clear in the trend that if we have a stoichiometric film, as evidenced by admittance spectroscopy, the device is stable. If it's super stoichiometric, it is not stable. So this is some more new data. Just like the XRD, this will be published soon. This is draft's nearly finished. And how do these stoichiometric effects really register on the surface, right? So to see exactly what they're doing on the surface, not more collectively, grossly in the bulkous perspective like you see with XRD, we utilize XPS, X-ray photo electron spectroscopy. And what we're doing here is we are taking two different stoichiometries of perovskite. So a lead to iodide ratio of 3.8 versus a lead iodide ratio of 2.8. So 3.8 being super stoichiometric and 2.8 being what we call near stoichiometric. It's within the air of the fitting of the XRD or the XPS system. So 2.8 plus or minus, 3.8 plus or minus. And then we bombard these samples under constant XPS measurement with blue light and see how the samples change. Now, I'll bring your attention here to the bottom of the screen. And you can see we have the two samples are actually remarkably different. And so the super stoichiometric composition here has a weak red edge versus the stronger red edge of the near stoichiometric material. Now you take that up here. So that's to link this back to the previous conversation. Expose it to blue light under constant XPS measurement. And you can see that the formamidinium lead iodide in blue decomposes while the lead iodide grows and then eventually decreases, but then the lead zero grows in. So direct evidence from XPS that we're actually forming lead metal at the surface as the lead iodide decomposes. So this is exactly what we saw in the XRD measurements, but we can see discretely where it's forming there on the surface via XPS. Now, if you compare this to a near stoichiometric composition, nothing really happens, right? The lead iodide, there's a little bit in the initial measurement. That's from fabrication. It doesn't really increase. It decreases just a little bit. Doesn't decrease a lot, just a little bit. We see the growth of a lead zero signal there in the green, but not a lot, just a little bit. And the perovskite persists quite strongly. I will also indicate that if you did this with red light, you would see no decomposition at all, or even less. The blue light tends to drive the degradation. If you want to know why, you'll need to read the paper when it comes out. I'm just giving you a little teaser here. But what we believe is happening is that since this is photo aggregated, that we have some sort of photo-mediated reaction where you have 3 lead iodides plus light can make a triiodide molecule plus 3 electrons. Those electrons can then react with the lead to reduce it to form 3 moles of lead for every 6 moles of iodide consumed. So not only does this consume the iodide material, which is bad, right? So as we described before, you cannot lose your Fa or your I. We're consuming it by this photo-mediated reaction, but then further converting the lead into lead zero making this a far more difficult reaction to reverse. In this particular environment, you would call this irreversible. Now, so that's the material stuff. So how does this affect devices? So let's get into a little bit of device data. And so we use, again, the PIN architecture highlighted in the green box. We also like to utilize slot die coating and doctor blading with the FAPBI3 material. Now, what we actually have in our stack, some of that is known, some of that's secret. The chemistry itself is quite close to the chest. I won't reveal what's in there other than it contains FAPBI3 and a dash of something else. Now, how do we make our devices? Again, slot die coating and blade coating. Here's a little indicator here. So in a PIN architecture, we'll first coat the hole selective contact, coat the perovskite anneal to form the perovskite in situ. The orange here is to represent a precursor film that's formed on the surface and then requires annealing to have a fully formed perovskite. On top of that, we will coat the electron selective contact and finalize it with thermal evaporation of some back electrodes or sputtering, what have you, but deposition of back electrodes and then full encapsulation with back glass and an edge seal. And there's probably some laminate stuck in there too in this sandwich. So this is a representation of our newest modules, the 150 millimeter modules we're making. So trying to replicate a standard kind of form factor that's in silicon. So something that the community can relate to. This is how, in a nutshell, we are making them. So on to durability of the cells themselves. So these are all 50 millimeter size substrates, not the 150. So 50 millimeters on a side. Forgive my hen scratch. Test architecture here off to the left. And so what we want to highlight is there is a piece of glass on top of the stack, but it is not hermetically sealed. The sides are still fully exposed, and so egress is no problem. The water, vapor, what have you, oxygen can just quickly run through an epoxy or a laminate back cover and have full access to the device from the side. Well, with that test architecture, we have submerged these devices that you can see here in some water on the video. Hopefully that is for you. But more importantly, things that are more aligned with the kind of IEC type test, but IEC plus, because we don't have a fully packaged or mailed device, is that we have 1,000 hours at 85C, and the cells are able to maintain more than 90% of their total power output. Further, we can take 85C, combine it with 65% relative humidity, also maintain more than 90% of their power over 1,000 hours. Further, light plus heat, so UV light plus heat, and then one sunlight plus heat. And we have these devices quite stable and quite durable, maintaining 9% of their power under all those conditions. And I will tell you, I think I've evidenced this very strongly in the previous slides. Every time I showed degradation, there was AU involved. So light is a strong driver of the degradation. And so this last test was one of the harder ones for us to pass. It took special chemistry to stabilize the material fundamentally to be able to pass this test. So it's not something you can package out. I can package out humidity, I can package out oxygen, whatever else cannot package out light or heat. So an example of this durability data. So you can see over the course of 1,000 hours, concurrent one sun and 75C. We have some cells that drop down to about 80% of their power, and some that maintain more than 90% of the power. But I want to show you several different examples so you can see kind of the gamut. Of course, there are some that do this, but I'm not going to show you those. I showed you some earlier. We don't need to get into that. But we know we have demonstrated that these cells can be made quite durable, particularly with our latest configuration, device architecture, and chemistry. That new chemistry and architecture will reside in this area. Our older configurations will reside in this area. And to show you what happens during degradation, we have a spectral response plot here in the lower right-hand corner. And so you can see the solid lines are the spectral response of the device before testing, before light plus heat testing. The dashed is after. And you can see that the dash and the solid more or less superimpose. The integrated current densities highlighted here in milliamps per centimeter squared are virtually identical. Some actually go up a little bit, but the material is maintained. We're not actually showing any degradation of the perovskite material. The current density is maintained from time 0 to time 1000. If you had decomposition, typically what we see is it's elsewhere in the device, usually at an interface or an electrode surface, something of that nature. So it's the device itself that tends to fail under these stress tests, not the material. That's something I wanted to highlight. And we believe this is, again, large part because of our chemistry approach. We are making the material itself as fundamentally robust as possible and then designing a strong architecture around it. Now on to efficiency. Everyone wants to know about the efficiency. This is important. And so, as I mentioned in the beginning, you have to have both these things in the same bucket. Right, so you can't have durability without efficiency or efficiency without durability if you want to make a product. And so, as I like to promote us, we have the most durable devices, but at a respectable efficiency. In this case, I call respectable 18%. I like to present our efficiency data in stabilized power output or steady state format to show that this is persistent efficiency. This is not just scanned efficiency, which a lot of people in this call will know can be manipulated. We also further like to toggle the light to look for any transients. So light on, light off, light on again. And so if there was some sort of light soaking effect, you would see a transient here when you turn the light back on. That would be something with a slope, not asymptotic transition, as you see in all three examples. So power, current, and voltage all display the same effects. Further, this cell also has a very small thermal coefficient. We measure around negative 0.03 to negative 0.05, typically somewhere in that range. And we'll show you how we do that here on this next slide. So we've built a large number of systems. I didn't actually mention this earlier. In our lab, bespoke systems, not really bespoke, but bespoke to PV, really, not to perovskite. But we have these specific systems that we've built to test durability. We've taken an architecture and other similar architectures and developed other systems. So the one that I showed previously, this is a temperature-controlled stage with persistent white light and electronics, so we can make constant measurements, regular measurements over a 24-hour period, over 1,000 hours. So about 6 weeks worth of time, but everything is concurrent and persistent. In this case here, we take a similar setup and we can actually modulate the temperature over time, as you can see here on the top curve. And what happens, right? So we start from 10 Celsius and heat to 70 Celsius. Now, if we were silicon, or as is published in the Series 6 data sheet online, you would see a significant drop in power, something of this very exaggerated nature. It's not that low, but there would be a significant drop in power as the system were to heat. In our case, we see the requisite drop in voltage as expected by physics. There's a small drop, but our fill factor, again, also a little small drop, but our current density completely flat. So overall, we do have a negative thermal coefficient, but a small one, about an order of magnitude less than that of silicon. Not quite, maybe 8x, 7x, 9x, somewhere in that range, but it's quite robust. So what does this mean? Why is this important? Obviously, the temperature cycles throughout the course of the day. As the panels heat up, they produce less power. And produce less power over time, that's less energy. So if you have a smaller thermal coefficient, you have 3 panels of equal nameplate power output, and the one with the smallest thermal coefficient will produce the most energy throughout the course of the day. So this is on the lab scale. We have not moved this up to full commercial scale, 2 meters by 1.2 meters. So there's a big fat Barry Bonds asterisk on that. However, if it persists from the lab scale to commercial scale, the perovskite panel will produce more energy throughout the course of the day than any of the competition. Now, another aspect of durability is that typically when we do durability measurements, they are accelerated lifetime tests, meaning we are stressing the cell in a way that hopefully we can collect a vast amount of information on how the cell will perform over time, but in a short amount of time, And so in this case here, we wanted to more replicate the day-night cycle. So we hold our cells at 55C and 1 sun throughout the course of the day for 12 hours, turn that off, cool to 25. So off for 12 hours, on for 12 hours, what happens? What I want to highlight, we have 3 different substrates with 6 solar cells each here. And these are not special cells. These are like leftover extra ones. This is a test. I actually found these data kind of hidden yesterday when I was looking because we hadn't really been highlighting this. This was just a test we were doing on the side for fun. And it turns out it's quite remarkable because these are leftover cells we had nothing better to do with. They weren't purposed for another durability test. The better ones we make, more focused ones go into durability testing. These weren't destined for that. But if we do day-night cycling, you can see they are quite robust. They're really flat over the course of 1,000 hours. To me, this highlights that self-healing capability, that when you're testing these perovskite solar cells in persistent conditions, high temperature and high light flux, that whatever occurs, oxidation, whatever, ion migration, is irreversible and it accumulates over time. So these cumulative effects actually make the device fail faster. It's this chicken and the egg argument, right? Where if you incubate a chicken egg, you create a chicken. If I want to create a chicken faster and I want to put it in boiling water, I have a hard-boiled egg. I don't have a chicken. And so even though we feel like our accelerated lifetime testing is valid, there's perhaps a hard-boiled egg that gets produced every once in a while along with some chickens. And so kind of take a step back from that and make it more realistic. We can see that if you give the chance to rest overnight without heat, without light, as would be occurring in nature, the perovskite cell, this indicates is vastly more durable than we're actually giving it credit for. Not going to carve that in stone. I don't have a piece of granite in front of me chiseling away, but it does indicate this may be a self-healing mechanism that really extends the lifetime of the device. Very quickly to wrap up so I can leave some time for questions, that we're working on 150 millimeter modules currently. So 50 millimeters is where most of our data has come from today presented. Here's a shot of a 150 millimeter module, one of the first ones we produced, and then a prototype frame to go around it for demonstration purposes. We're making another one out of machined aluminum right now as we finalize the prototype demonstrator. As we scale to 150, obviously we have a 9x area increase from 50 to 150. So how do we compensate for this in our coatings? And so you can see here kind of early stage coating on the left. So you have these smearing marks, Marangoni effect. Coating didn't work out so well. We have a second sample here. It's got scratch marks on it for profilometry. But clearly, there's a color gradient, which means the thickness is not persistent. So we have inconsistent chemistry, as noted by the photoluminescence image on top, and then inconsistent thickness, as noted here by the color gradient. Then we modified our processing parameters a bit, modified the chemistry a little bit. Now by PL imaging, we have a very homogeneous coat, particularly compared to what it was, and then the gradient is all but gone. Further, that is composition. This is the stoichiometry we're talking about, but what about the bulk property, the crystallites? And so we take a similar substrate, cut it up into 9 sections, observed all of them by XRD, and you can see they all have the same pattern with an ITO background reference. So crystallographically, structurally, the material is the same across all 9 areas. And with that, I do want to conclude again to leave some questions for time, but not without thanking everybody who's involved. Again, I know I'm giving this presentation, but I didn't do any of this work. This team here that's fantastic did all the work. They're quite wonderful, quite industrious, and quite intelligent. And I'm very, very, very lucky and blessed to work with them. I'm also lucky and blessed to work with the Enroll team, particularly Joe Barry. We've had a great relationship that's been very conducive for both of our careers. He's helped promote this work. He's helped drive it. He's given me inspiration. great guy. And then last but not least, the Hunt family. They're true believers. You know, they value themselves as an energy company. We all need energy, right? You on this line may not necessarily care for oil and gas. That's an opinion that varies geographically in all the kind of ways, but they're an energy family at their core. And they've been very supportive and very wonderful to work with. And I really thank them for the opportunity to even get this far. And then finally, a gracious audience. Thank you for your patience, and I'm very happy to take any questions.
Thank you very much, Michael. I also wanted to mention Michael is, or Dr. Irwin, I should say, is one of the advisory board members, and today's US MAP presentation is being held in jointly with the Energy Frontier Research Center that we do at NREL on CHOICE, the Center for Hybrid Organic Inorganic Semiconductors for Energy, which Michael is also a advisory board member of, and so we have a lot of attendees from that group as well today. So with that note, I will turn to some of the questions. One comment I'll highlight that before we get into the questions was the kudos that were given on the Barry Bonds reference. So well done, Michael. That was noted by a little bit there. Yeah, that was noted by at least one or two of the attendees. So so let's go back here. I guess one question that that came up that I think is an interesting one is, let me find it here. It was near slide 18. You mentioned the importance of the super stoichiometric and amorphous phase. The question is, what evidence for this is there, and well, you know, where is this phase located? Grain boundaries, interfaces, or bulk form? And maybe you'd like to discuss that a little bit.
Sure. So again, my belief is that this super stoichiometric material exists at the surface. These are calculations that are ongoing in our DFT group, but when you do have excess FAI, you can have some of it exist in interstitials. An iodide interstitial is highly feasible, form something like an H center or a V center, so maybe like a diiodide bridging an X site in an interstitial. So you can house a certain composition, or a certain percentage or concentration of FAI into the structure, but not nearly to what we see, meaning that the super stoichiometric material as represented here must exist on the surface. And this representation here is to show there's an exchange, right? So if n equals 1, you have just FAI, right? And that FAI can actually, there should be a second arrow here, the forward and the reverse reaction of FAI going in and out of the material. So if FAI goes into the material, you actually convert this structure, the crystalline structure, into this amorphous structure. And if excess FAI leaves, then this amorphous material becomes crystalline, right? So there's a cycle there, a symbiosis that may actually be important for the stability of the material, where if you have the right amount of the amorphous material at the surface, it acts as a well for FAI exchange. That if you do form a defect, which I've highlighted several times, these defects are real, right? Go back up on this structure here. Yeah, these defects are very bad, right? They direct to the decomposition of the Perovskite by our calculation. So if you have this well of FAI at the surface, you can satisfy those vacancies and maintain the durability of the film. So if you don't have any of this amorphous material, the film is likely destabilized. And the evidence, again, here is through XPS. We can see that if you have super stoichiometric, it decomposes quickly. Just remember this, we're only measuring down about 10 nanometers into the film, versus if we have stoichiometric, the film does not decompose. So that's what I consider the evidence, the direct evidence at the moment. We're working on DFT calculations to further support this.
All right, I'm gonna go to a question from an international attendee. And and was wondering if you could comment on if you have at Hunt Perovskite Technologies a roadmap for PCs, you know, up to 29, i.e., are you thinking about Canon devices and this kind of thing, and what thoughts you might have on that front?
Yes, we do actually. I anticipated a question like this quite some time ago, and so we've been doing some modeling work, like SCAPS, for example, to see the feasibility to 29%. And after some extensive modeling work, we can answer yes, 29% for a single junction cell, no tandem, is completely and totally feasible. The Shockley-Queisser limit for this band gap is 33%, or maybe 32, depending on how you count. But we believe that 29% is totally achievable with this material. How we get there is yet to be seen. We still got to get there, but it is absolutely achievable. And yes, we have a roadmap to get there.
All right, let's see here. I guess, I mean, there are a number of questions coming in, so I'm trying to pick ones that might be kind of the most apropos given some of the subject. But another question that you kind of touched on was related to the IEC tests, and why do you think the IEC tests are relevant given that the acceleration factors for perovskite degradation modes are likely different than those in silicon modules? And have you done any work to define perovskite device acceleration factors?
Great question. And I totally agree. I feel, not everyone shares this opinion, but I feel the IEC test is simply the barrier to entry to better sell your modules on the market, right? So is your cell good enough in its initial state? And I don't feel that IEC testing is really representative of what it's required to get a perovskite solar cell to 20 plus years module durability. And so part of that is that, you know, the IEC is accepted, right? So we do root ourselves in it, but, you know, there's some significant changes, right? So this persistent light test, for example, is not part of the IEC. There are other things we do that are also not part of the IEC, but inspired by the IEC in some way, I would suppose. Further, our cells are not hermetically sealed, right? So an IEC test is typically a module that has standard packaging. It's tabbed and everything else. So for example, the freeze-thaw cycling in the IEC test is to test the solder durability. So typically the solder will delaminate or crack, and then you'll lose connection to the cell. We obviously don't care about that because we don't have contacts yet. We don't have tabs. We just have contact pads that are thin metal. We have pogo pins that connect to them all individually. So it's not an issue, right? And so absolutely yes. We're taking an Arrhenius type approach, looking at the different thermally or light activated degradation mechanisms, calculating their energies of activation, and then estimating actual device lifetime based on the Arrhenius equation or application to the Arrhenius equation. So we're digging down into that. So we want to get real numbers and understand exactly how long the device would last far beyond IEC testing.
All right. Well, listen, again, I'd like to just thank Michael for the nice presentation today, and all our attendees for the excellent number of questions, but not going to be able to get through more as we've reached kind of the end of our time. And so with that, I'll note we will be posting our information on the USMAP website, usaperovskite.org, for the speaker for next month. We'll probably take a break in December, but we'll be getting that information out shortly. Again, I'd like to thank Michael for his nice presentation and the audience for attending, and hope to see a lot of you again kind of in our next seminar. So with that, we'll close out and end today's presentation and webinar. Thanks very much.
Thanks, Joe.